Hello, Quest. Okay, so we're going to talk about something called simple harmonic motion. And I'm going to give you an example of what this is. So say we have a cart that we attach, and we have a spring connected to the cart, the other end is fixed to a wall, and say x equals 0 is the natural length of the spring. So that'd be an equilibrium at x equals 0. And we pull this cart over, I'm going to say x equals a. We pull it over here and release it. And, what's that going to do? Well, obviously, it's going to be pulled to the left. When it gets to x equals 0, the spring is relaxed. It's at its natural length where it wants to be. So the spring force disappears, but momentum is going to carry it further to the left. And now the spring is being compressed. So it's moving to the left, but the force is pushing it to the right. And we'll see that it's actually going to reach x equals minus a before coming to rest. It's kind of easy to see that from conservation of energy. If we ignore, here we have 0 kinetic energy, we release it from rest, but there's spring energy 1/2 Ka squared, and it's going to keep going until its kinetic energy is 0 on the other side. And so if there's no energy lost, it has the same amount of spring potential energy. So the spring has to be compressed the same amount. So if there's truly no friction, this cart is just going to keep on going back and forth. And we want to be able to describe the motion of this system, mass on a spring. So let's apply Newton's second law. Let's do F equals ma. Okay, now the force I'm going to write as minus kx. So we have to be a little careful when talking about the spring force because it has a direction. But let's say we pull it over to x equals a. Obviously this is our positive direction. A is a positive number. So we have negative to the left. And so we're saying the force here is negative. If x is positive, the force is negative, which is correct. If we're over here, the force is to the left. But then as we cross 0, it's slowing down now. X is negative, so if we plug a negative number, we get a positive force, which is to the right. And so this force gives us the right magnitude and direction regardless of where we are. Okay, so our goal is, to solve this, we want to be able to describe things like, if we release it here at t equals 0, what is the position of the cart as a function of time? Say we want to know position, velocity, and acceleration, all as functions of time. Now, we cannot use the kinematics from chapter 2 for this problem. Very easy to see why. If we solve for the acceleration, we can see that it depends on x. And so as this cart is moving, the acceleration is changing, and the kinematics we can deal in an algebra-based class. We can only deal with that case of constant acceleration. So we have to come up with another way of solving this problem. And we're going to do that in a kind of a roundabout way. So I'm going to manipulate this equation a little bit. First, let's add kx to both sides. We can rewrite it this way. ma plus kx equals 0. Dividing by m So Newton's second law applied to this system, we can write it this way. A plus k over mx equals 0. So I'm going to write that off to the side. I'll write it here for now. Okay, now how are we going to go about solving this? We're going to do this in a kind of a strange way. I think I'm going to erase this and just draw it a little bigger. Maybe I'll remove a few things as well. So we don't have to draw the spring. So we have our cart, which we can represent as a particle. And what I'm going to do is I'm going to draw a circle like this. This is called the auxiliary circle. And let's say that our cart starts out here at x equals a. And we can represent that with just a point. Yeah, we just erase the cart as well. So we have this point, and we know this point is going to be moving back and forth, but we want to be more descriptive than that. We want to be able to talk about, where it is at a given time, how fast is it moving, that kind of thing. So what we're going to do is we're going to consider x equals a. Let's draw a radius line here. So the radius here is a. And let's define this angle to be theta. And we're going to say that theta is equal to omega t. So what we're doing is we're picturing a line. So if t equals 0, theta equals 0, and our line is just along the positive x direction. But as time increases, this theta, this angle increases, going counterclockwise, but at any given moment, it is, theta is omega times t. And so we have this, we can look at this particle that's moving around this, it's called the auxiliary circle, with an angular velocity omega. Okay, so I'm going to look at the tangential velocity. We can draw that. We know this particle is moving in a circle, and so it has an acceleration towards the center. Here, we know the radius is a because, at t equals 0, it's going to reach x equals a. So we have an acceleration vector that points inwards and a tangential velocity. And we can also have a radius vector pointing to this point on the auxiliary circle, but I don't want to draw that. We have a radius line. That'll be good enough. And so what I'm going to do is draw this, these lines parallel to the x and y axes. And so if this angle's theta, that would make this angle theta. And this angle theta as well. And what I want to do is look at just the components in the x direction. So let's start out with the x coordinate of this particle. That one's easy. We have this triangle here with the radius a. So yeah, let's look at position. First, we have this triangle here where the radius is a, and we have our angle theta. So this would be a cosine theta, or a cosine omega t. So the x-coordinate of this point, a cosine theta, but the x-coordinate is a cosine omega t. So that's what we get from looking at the position. Now let's look at this velocity vector next. So remember for uniform circular motion, in general, for velocity, v is equal to r omega. And the radius is a in this case. So v is equal to a omega. But we want the x component of velocity. So this velocity vector has x and y components. We only want the x component. I'm going to write this here. So the x component of velocity, we have this velocity vector. This angle here is theta. And the velocity vector has a magnitude a omega, or the speed. The magnitude of the velocity, the speed is not changing. We created this circle, so this particle is moving with a uniform angular velocity, which means a uniform tangential velocity, which is a omega. And so this side, is the x direction is opposite the angle. So we have a omega times sine of theta. Now, the component is in the negative direction. So if we look at the x component, we have v is a omega, or minus a omega, because it's pointing to the left. So we have minus a omega sine omega t. Okay. And finally, let's look at acceleration. And yeah, we're focusing on the x components here. So the acceleration vector is pointing in this direction. So this angle is theta as well. We have, this line is parallel to this line, so those two angles are equal. Remember, for acceleration, basically we have v squared over r, where v is r omega. So the acceleration is r omega squared. The radius in this case is a. So that's what we have for acceleration. So this is our acceleration vector. It has a magnitude a omega squared. And the x component, again, we're adjacent to the angle. So we have a omega squared cosine theta. So again, if we just look at the x direction, we have the acceleration in the x direction. And again, the acceleration vector is pointing in the negative x direction. So we have minus a omega squared cosine omega t. So what I want to do is write these down together. I'm going to erase this. See if I can fit this anywhere. So, can review what we've done. We're looking at this point that's just circling around at t equals 0. We are at x equals a, and then we're circling around, and basically what we're doing is looking at the projection onto the x-axis. So at some arbitrary point here, the x-coordinate is a cosine omega t. If we look at the x component of velocity, minus a omega sine omega t, and the x component of acceleration, minus a omega squared cosine omega t. Let's do this. Let's write the acceleration minus omega squared times a cosine omega t. Now, what is a cosine omega t? That's x. So we have a minus omega squared x equals 0, or a, I'm sorry, getting ahead of myself here. So we have a equals minus omega squared x. And now we can move, let's add omega squared x to both sides. And we have this equation, a plus omega squared x equals 0. And so we have a relation between xv and a that solves this equation. And so basically, let's compare this equation to this one, and basically it is the same thing. So what I want to do is I'm going to move this equation over. For a mass spring system, Newton's second law tells us that a plus k over mx equals 0. And if we take this equation here, a plus omega squared x equals 0, let me say a solution to that equation. I want to say the solution. This is a particular solution to this equation. Now I say it's a particular solution to this equation because we started out with, if you point t equals 0, cosine of 0 is 1, x equals a. And if you just look at x as a function of time, it starts at x equals a. After a certain amount of time, we're going through this cosine function. And so the, cosine starts at its maximum value. If we plot cosine as a function of time, it starts out at its maximum amplitude and does this. And just keeps repeating that over and over, just like this cart on the end of the string is going to keep on going back and forth. If there's no friction, it'll just keep doing that forever. Of course, not realistic. There's always going to be energy dissipated. But we're ignoring that for now. Actually, we're going to continue ignoring that. But, so basically this is one complete cycle here. It starts at maximum amplitude, then here it's gone to 0. That would be, the cart's over here. So basically this mass on a cart problem, you think we can create this auxiliary circle and picture this point moving around counterclockwise, and as this point is moving around counterclockwise, the cart is moving back and forth, and their x coordinates are always the same. So like when this point on the auxiliary circle is at this position, the cart is here. When the auxiliary circle, when the point's over here, the cart's over here. It just, they always track. So if you were to like shine a light down on this point, it would match up with the motion of the cart going back and forth. And we can also see the velocity and acceleration as functions of time as well. But let's kind of go back to this particular system for a moment. What I'm saying is that this is a solution to this equation. So if you have that equation there, we know what the solution is. Now, for those of you that have had calculus, this is very trivial to check. Just going from, remember, velocity is the rate of change, it's delta x over delta t. Well, if you take the limit, you get the rate of change of x over t, or dx dt, the derivative of x with respect to time. So remember, derivative of cosine, you pick up a minus sign. Derivative of cosine is minus sine. And from the chain rule, you're differentiating with respect to time. So you've got this omega, which you pull out from the chain rule. And then the derivative of sine is cosine, so you don't change the signs here. But you pull out another omega from the chain rule again. And we can see that this is a solution. A plus omega squared x does solve that problem, that equation. Okay. And again, this is one particular solution where t equals 0. It's possible to have a more general solution where you can start t somewhere else. We don't care about that right now. We just want to look at the basic motion. Starting in a different time would just be moving our starting position. It's going to be the exact same motion, just start the graph in a different place. So we're going to look at this auxiliary circle approach. This is our solution to this equation. So now if we go back to the mass on the spring, let's kind of start from the beginning now. We won't redo what we have, but now we come up with this from Newton's second law applied to this problem. We can get it in this form, and then we say, okay, let's say that omega squared, let's just define omega squared to be k over m. And then we have that equation, and we have a known solution to that. And so we call this the angular frequency. And, of the system. And for a mass spring system like this, it's k over m. Let's do a numerical example. Say we have a mass of 500 grams. And let's say k is 12 newtons per meter. So I've made up these numbers. So in this case, we'd have 12 newtons per meter divided by 500 grams. Let's convert to kilograms. So 500 grams on the bottom. So we have kilogram here, 1,000 grams on top. That works out. And then, that's it. Now let's do this. A newton is a kilogram meter per second squared. So let's look at the units. We have newtons, kilograms, and meters. On the bottom we have meters, kilograms, newtons, and second squared. So everything else cancels out. So omega has units radians per second. So again, that would be the angular velocity of that particle moving around a circle. We'd measure that in radians per second. So we know how fast to spin that thing around. Then we can look at the projections to figure out where it is. But we're not going to bother drawing these pictures. This is on the equation sheet. So you can just use that whenever you come up with an equation like this. Now, this kind of was a fair amount of work to kind of get to this point, where we have a solution to this one particular problem, like a mass on a spring. Do we really care about a mass on a spring? And it turns out, that's actually an interesting problem in its own right. But more than that, we're going to look at another example later on. I will do that in a separate video. We're going to look at a pendulum. So we have a pendulum. you just have like a mass on a string, and you pull it aside, and it's just going to go back and forth. And we're going to show that that's simple harmonic motion as well. At least in some cases it is. And so that's another example of this type of equation. Now, I once saw an article that had 21 like non-trivial examples of this equation showing up in physics. I tried to read it, but they wanted money, so I didn't bother. But this equation actually is way more important than it might look. This idea of simple harmonic motion, extremely important. Like if you study mechanics, you have a whole chapter on talking about simple harmonic motion, just like a mass on a spring. When you get to study electricity and magnetism, although you won't do this in 122, it would be slightly more complicated circuits than we can deal with. But if you want to talk about like the current in a circuit, you get equations just like this. We have different variables, but A and X are not independent. These two variables are related to each other. Like A is delta V over delta T, and V is delta X over delta T. So there's, these are not just two totally independent things. We could even write this in terms of a single variable X. That requires notation that we haven't done before, so I'm not going to bother with it. But just know that there's a connection. A and X are related in a very particular way. And so, yeah, this kind of equation shows up all over the place. So yeah, you'll have like a whole chapter in mechanics devoted to this. Electricity and magnetism, like oscillations in electrical circuits follow this kind of behavior. Electromagnetic waves. If you ever take a class in quantum mechanics, you have a whole chapter just on simple harmonic motion. Very, very important topic overall. Way more important than it might seem just looking at a mass on a spring. Okay, now let's analyze this a little bit. I never even got the number out of this. I just checked the units, but that's fine. But let's look at, I'll draw this a little bit bigger. Let's plot the position as a function. Like, normally we want to plot it as a function of time, but let's plot the position, say, who cares what the units are? Let's plot it in units of omega t. Okay. Oh, probably shouldn't put the parentheses there, but because what we're plugging in the cosine isn't t itself, it's omega t. And so if we just plotted, if we just multiply our time values by omega, now this is dimensionless. We have radians per second times seconds, so this is just a measure of radians. But let's look at some certain values. Let's actually make a table here. Let's say omega t, and let's look at both sine and cosine. Okay, so 0, let's look at pi over 2, pi, 3 pi over 2, and why not put 2 pi? Now, 2 pi, we're just going to be repeating 0. We've gone all the way around the circle, so whatever we get here, we'll just put it down there. But sine of 0 is 0. Cosine is 1. Cosine of 0 is 1. Then for pi over 2, flip it. So again, you can think of this unit circle where a cosine, the coordinates of that point are cosine theta and sine of theta. And so for sine of theta, we look at the y-coordinate. So if we're at pi over 2, that's 90 degrees. That's a maximum value of 1. And then when we get to pi, we're back to 0. 3 pi over 2, we're here, that's negative 1. And then 2 pi, we're back to the start. So here we have 0, pi over 2, pi, 3 pi over 2, 2 pi. So if we just look at sine, we're looking at the y-coordinate. So we're 0, 1, 0, negative 1, 0. For cosine, we have 1, 0, negative 1. And then 3 pi over 2, the x-coordinate is 0, and then we're back to 1. So if we plot this, let's break this up into pieces. Here we have, we're looking at like pi over 2, pi, 3 pi over 2, 2 pi. Okay, so and let's say 1 and negative 1, and I'm going to draw this dashed horizontal line, just so I draw it a little more accurately. Okay, so here, if we're plotting position, actually I'm not even going to put this here. We'll see why in a minute, but this is 1, that's negative 1. Actually, I'm going to call this A and negative A. Okay, so if we're plotting position, we start at 1, and then we're at 0, and then negative 1. So just to get a fairly accurate plot, we're going to look like this, and then just repeat the exact same picture over and over again. Okay, so this is position as a function of time. Now let's look at velocity as a function of time. So the amplitude is now a omega. So let's say omega is a little bit bigger than 1. So let's say that this is a omega. We can plot everything in the same graph. Now velocity, we're looking at sine, but we have a minus sign in front. So we're going to actually go 0, negative 1, 0, 1, 0. So we have 0 to start with, and then negative 1, back to 0, 1, and then 0. So our velocity is going to look like this. So remember we started out at rest? We released this cart from rest, so our velocity is 0. And then the cart started moving to the left, so its velocity is negative. And then here we get maximum velocity. This is where x equals 0. We have our maximum velocity. So remember when x equals 0, it's been accelerating the whole time until x equals 0. That's when the force disappears. And so we stop accelerating, and then moving past that, we would be slowing down. So we're accelerating in the negative direction until we get to x equals 0. And after that, we're slowing down. So this gives us our maximum amplitude of velocity when x equals 0. Similarly, when x is at its maximum extension, the velocity is 0 because it stops at maximum extension. So when the amplitude is, or when the position is at its maximum amplitude, the velocity is 0. And then here, 3 pi over 2, that's when we're, the cart itself. So remember, it's a projection on the x-axis. So here it would be like this. We're back at x equals 0 at maximum velocity. So at 3 pi over 2, we're at x equals 0. But we're at maximum velocity to the right. And so now we're stretching the spring, and so it's pulling back and we're slowing down. So we've kind of gone through this full cycle here. Okay. Why don't we do acceleration while we're at it? So we'll have a new amplitude here and a new color. So it's red. So let's say this is a omega squared. this would be minus a omega squared. And now we basically have this cosine plot, just with a different amplitude, but now we have a minus sign in front. So we're going to have minus 1, 0, 1, 0, minus 1. So we're going to start at negative 1, and then go to 0, and then positive 1, 0, and negative 1. So the acceleration plot is going to look like this. So this would be acceleration as a function of time. So if we look at t equals 0, we have a very large negative acceleration. And that's because, I'm going to draw this again here. So here x equals a. Here x is negative a. So again, we start out with the cart over here. And so the string is very stretched out at this point. It's exerting a large force to the left. And so that would be a large acceleration to the left. Now when we get to x equals 0, we should expect the acceleration to be 0, because the force is 0. So when the position is 0, acceleration is 0. See that in both cases. And then over here, now when we cross 0, the spring is being compressed, and so the force is increasing until we get to x equals minus a. That's maximum extension. And so now we have a large force to the right. So here we have maximum acceleration in the positive direction as well. And so this graph kind of has everything. Okay. Now, I want to talk about one more thing. I think the plan is I'll talk about one more thing. And again, there's a lot to absorb here. So what I'll do, one more topic, and then in a separate video, we're going to go over a problem in some detail. I'll just make up a problem, and I'll do that in a second video in case you want to go back and just look at the problem. And then we're going to talk about another example of simple harmonic motion. So let's look at this graph again. Let's just we can look at anything, but I think position will be easiest. We start out here, and after this, when omega t is equal to 2 pi, so if we look at this point here, we have completed one cycle. We're back to x equals a. So we started at t equals 0, we're here at x equals a. And then when omega t is 2 pi, we're back here. And so we call the time it takes to complete one cycle the period and use a capital T. So we can say that omega times capital T is 2 pi. And that's an important relation. So I'm going to put a box around that. I'll just write over here, omega times the period is 2 pi. And we can just see that from the graph and from the definition of what a period actually is. Now, it's kind of a nice way to write this. Now, t is a period in seconds. That's the time to complete one cycle. If we take the reciprocal of that, so this would be like seconds per cycle. If we look at the reciprocal, we're talking about cycles per second. We call that frequency. So we define frequency to be 1 over the period. So that's just how frequency is defined. So period is in seconds, frequency is in cycles per second. Now it actually has its own special name called the Hertz. It's named after a guy named Henrik Hertz, which should learn a little bit about him in 122. He was the one that was able to experimentally confirm the existence of electromagnetic waves. That was a really big deal. And he was able to create waves and build a detector to detect them. Yeah, so they named this unit after him. Okay. And if we plug that in here, T is 1 over the frequency. So we have omega over the frequency is equal to 2 pi, or omega equals 2 pi times the frequency. So omega is called the angular frequency, which is measured in radians per second. Frequency is cycles per second, and they're related by this factor of 2 pi, because one cycle is 2 pi. Now, just a quick review of, we'll do a very detailed problem, but now if we have a mass spring system, given the spring constant and the mass, we can find omega. I think I erased that. Let's put a box around that as well. For a mass spring system, we know that omega squared is k over m. And we know that omega is 2 pi times the frequency, and frequency is 1 over the period. So if we have k over m, we can find the frequency of the motion or the period. How long is it going to take to complete one cycle? We can do a lot more than that, but yeah, that'll just come up when we do a problem. So I'll do that in a separate video so it's easy to find, and this one is probably gone on long enough. So I think we'll stop this one here and make a couple more. This is kind of a long chapter.